on this slide we talk about projective space. So we will write projective space as P and K, where K is closed. So what is this projective space? Now it is nothing but a set of equivalence classes of some tuples. So let me write this down. Set of equivalent classes of these n plus 1 tuples. We are talking about n space, but we are taking this n plus 1 tuple, and each of these ai lies in K, which is closed. So you identify a0, a1 all the way to an with this lambda a0 all the way to lambda an. This lambda is not 0, and lambda is an element of this closed field K. So lambda is an element of K and lambda is not 0. So you write it like this. You take K n plus 1 minus 0, obviously since lambda is not 0 and 0 is not here, and you take all these points and you use the equivalence relation. Yeah, so this is not the right place to learn about projective space. You should have already known about it. If you do not know, just look it up in Wikipedia or some other geometry books and get a fair idea of it. So what it essentially is, there are lines through the origin, and to each line you associate a point. Yeah, so this is easy to understand in 2 space. So for all these lines through the origin there are, and to each of these lines you associate a point. So there is a good book in geometry published by Open University, and I think one of the authors is Jeremy Gray, and that is an extremely good book to learn about projective geometry. At least know about what it is if you have not seen before. At least I learned it from that book, and it has all its exercises solved in the back and easy to learn. So again, the book is called Geometry, published by Cambridge University Press. Actually, you will find it in the Cambridge University bookstore. So again, this is an n plus 1 tuple, and this is called homogeneous coordinates. So if you have not seen projective space, get Jeremy Gray, Geometry, published by Cambridge University Press. So this n plus 1 tuple is called the homogeneous coordinate for the projective space. So now we should talk about graded rings. Idea is this: you just, instead of using normal polynomials which we used in affine space, we want to use homogeneous polynomials, and we are just laying the framework for using the homogeneous polynomials. So we have to talk about graded rings, and this grading is nothing but corresponds to the degree of the polynomial. So here this n stands for natural numbers along with 0, so 0, 1, 2, 3, and so on. So S is a direct sum of some abelian groups. These abelian groups are S0, S1, S2, so on, and SD, say a particular abelian group, is called abelian group of degree D. So you should always think of graded rings, or at least I always use the crutch of homogeneous polynomials. So the dth part is degree D. So I think of dth part as degree D homogeneous polynomials. So otherwise they are called abelian group of degree D. And then again, just like multiplication in homogeneous polynomials, you have ST times SE. This is a subset of SD plus E. So think homogeneous polynomial multiplication. So we are just laying down the framework to use homogeneous polynomials. So instead of normal polynomials, we will use homogeneous polynomials, and everything else remains the same. The way we define algebraic sets, closed sets, open sets, and so on. So S is equal to, say, S0, direct sum S1, direct sum S2, direct sum S3, direct sum S4, and so on. So S0, say, degree 0, so just K. S1, degree 1, so generated by x comma y. Element could look like 2x plus y or 2x plus 3y. S2, so it is generated by elements of the form x square, xy, y square. Yeah, all of these have degree 2. So again, elements of S2 should look like 3x square plus xy. Now S3 will be generated by x cube, y cube, x square y, and xy square, and so on. You can think of, yeah. And then you see, you multiply two polynomials, 2x plus 3y times 3x square plus xy. So you should land up in S3. Obviously, you multiply it together. You multiply two homogeneous polynomials, you get a homogeneous polynomial, and you can prove these facts if you want to. So now we talked about homogeneous polynomials. Just like in previous polynomials, we talked about their ideals. We want to talk about homogeneous polynomial ideals. So I will just write down first the framework, and then again you should think of homogeneous ideal as generated by a bunch of polynomials, and each of those polynomials is homogeneous. So yeah, so the polynomial A would have a bunch of polynomials of different degrees, and that's why I'm going to write it as, say, A intersection Sn, or I'm writing St here, so I should write direct sum D element of n, but I think it is clear. So think of it as a bunch of homogeneous polynomials. Yeah, not necessarily of the same degree. So for example, you could have x square plus xy, y cube. So there are three homogeneous polynomials, and all three have same degree. So if you do not know what a homogeneous polynomial is, I think the best way to look it up is in Wikipedia. Yeah, you should know the difference between a normal polynomial and a homogeneous polynomial. So now let us list some facts from commutative algebra. Now, everything here is taken from Hartshorne, so you should be able to read up on it. So we're just talking about sum of homogeneous polynomials, product of homogeneous polynomials, yeah, intersection of, say, homogeneous ideals, radical of homogeneous ideals, and also like sum and product of ideals. So you see, sum, product, intersection, and radical of homogeneous ideals is homogeneous. So second point is, we want to talk about homogeneous prime ideals. Ultimately, we would want to link up irreducibility with prime ideals, just like in the affine case. And here we will talk about homogeneous prime ideals. So you take two prime ideals, f and g, both of them are homogeneous, both of them belong to ideal A. That implies either f belongs to A or g belongs to A, just like in the affine case. Only difference is f and g now are homogeneous. So we need homogeneous polynomials because of this property. Say f is a homogeneous polynomial of degree d. Then you can take lambda out, and this is what you will get. Now see the 0, right hand side is 0 if and only if left hand side is 0. So homogeneous coordinates, zeros of f depend only on the homogeneous coordinates. So we can talk about zeros of polynomials in projective space, and when you talk about zeros of polynomials in projective space, you are essentially talking about homogeneous polynomials, because otherwise it would not make any sense. So they depend, so zeros of f depend only on homogeneous coordinates, precisely because f is a homogeneous polynomial of degree d. Now fix T a finite subset of this graded ring S. Yeah, so suppose T is generated by a finite set of polynomials. See, or T is just a bunch of polynomials f1 to fr. Now even if T is an infinite set, says S is a Noetherian ring, so S is a graded ring, and T is composed of these f1, f2 all the way to fr. Each fi is a homogeneous element. Now even if T was infinite set, since S is Noetherian, it will be generated by a finite number of elements. So let me write this down. Even if T is infinite, because S is Noetherian, it is generated by a finite set. Just like in the affine case. But now we talk about homogeneous polynomials. So that is why we can always talk about T as a finite set. Now vanishing set of homogeneous polynomial f, or zeros of f, is just precisely what it was before. All the points in the projective space where f of p is 0. Again, you want to talk about zeros of t, that would mean zeros of or variety of t or vanishing set of t. It's just the common zero of all these polynomials. So all the fi's have to vanish. Yeah, so I should actually write fi p equals to 0 for all fi in t. You always could also write it like as zeros of f1 comma f2 all the way to fr, where each fi is homogeneous. So again, this is taken from Hartshorne, and you should be able to read up on it. So instead of z, I can write vanishing set. On this slide, we talk about algebraic set and Zariski topology. So let us first define an algebraic set. Say you fix a set Y, which is a subset of the projective space, and you call Y a algebraic set. Yeah, if it is defined as the zeros of certain homogeneous elements. Yeah, so going to formally write it from Hartshorne. So Y, a subset of Pn, is an algebraic set if there exists a set T of homogeneous elements of S. Yeah, where S is the graded ring, such that Y is the zeros of T or vanishing set of T. Yeah, so same as in affine case, polynomials are just replaced by homogeneous polynomials in the projective case. So the following are algebraic sets. So the following are algebraic sets. First is union of two algebraic sets. So that also means a finite union of algebraic sets is an algebraic set. Then intersection of any family of algebraic sets is an algebraic set. And empty set and whole space are also algebraic sets. So you see immediately once you define a closed set as an algebraic set, so if you say closed set as an algebraic set, then you have Zariski topology. Yeah, you have all the conditions satisfied for it. So a finite union is there, arbitrary intersection is there, empty set and whole space. All of these are algebraic sets. So let us give some examples. Whole space, again just as an affine case, I will say 0 equals to 0 defines the whole space. So vanishing set of 0. What about empty set? Now, empty set we will define slightly differently. So we want to talk about something called the irrelevant ideal. So consider this maximal ideal generated by say x0 all the way to xn in, we are in space Pn. Now this ideal, the vanishing set of this ideal is the null set. Why so? Because x0, x1 all the way to xn, this ideal would vanish only on the point 0, when all the coordinates are 0. Only then this set will vanish. Yeah. So because anyway it will have a polynomial which will be x0 plus x1 plus x2 all the way to plus xn. So that polynomial will be in this maximal ideal, and that polynomial will vanish only at the point 0, 0, 0, 0, 0. But that is not in Pn, and therefore the vanishing set of this ideal is null set, and we call this irrelevant ideal. Yeah, so you have to keep this in mind, and this term is thrown around very often, and you should immediately know what we are talking about. So now points are also algebraic sets in Pn. So points are algebraic sets in Pn. So we have already shown whole space, empty set, and let us now talk about single points or homogeneous coordinates. Yeah, so this tuple will have at least one of the elements as non-zero. Yeah, by definition, not all of them can be 0 because the 0, 0, 0 tuple is not even in projective space. So at least one is not 0, and without loss of generality, you just pick up as A0 as non-zero. Yeah, say A0. So now you divide everything in this tuple by A0. And now we rewrite it as 1 comma P1. I just writing A1 by A0 as P1, P2 all the way to Pn, and now we will write its vanishing set. Yeah, so we have to write a bunch of homogeneous polynomials whose zero set is precisely this. So we are going to write degree 1 polynomials. So x1 minus p1 x0. So x0, if you plug in the above homogeneous coordinates, you will get p1 minus p1, which will be 0. Similarly, x2 minus p2 x0, plug in the above homogeneous coordinates, x0 is 1, x2 is p2, you get p2 minus p2 is 0. Let me write this down. So this will be p1 minus p1 because x0 is 1 and x1 is p1. Similarly, we will have p2 minus p2 because x0 is 1 and x2 is p2, and so on. So you see that the points are also algebraic sets in Pn. Now for Zariski topology, everything has been covered in proposition 2.1. So you just say that algebraic set is the closed set. So open sets are complements of algebraic sets. So let me draw one. So you first have a algebraic set X, and then you take a finite number of points out of it. And what is remaining, so after from you remove these 4 points in fluorescent green, and you get a open set. So for F homogeneous, it is obviously all those points of V where V is a projective algebraic set where Fx is not 0. So this is the projective algebraic set. It could be a small space like a circle, or it could be the entire space. So V is a projective algebraic set. It could be the whole space or a small set like a circle. Yeah, circle means circle with homogeneous coordinates. So it should be x square plus y square equals to z square. So now we want to define a projective variety. So this is irreducible algebraic set in the projective space with induced topology. And open subset of projective variety is the quasi-projective variety. So let us write down what I just said. So it is irreducible algebraic set with induced topology. So open subset of projective variety is a quasi-projective variety. So one of the last things I want to talk about on this slide is homogeneous ideal, and then the corresponding homogeneous coordinate ring. So homogeneous ideal, so F belongs to the graded ring S. F is homogeneous. And F vanishes on all points of the set Y. So this is homogeneous ideal associated with the algebraic set. So just a bunch of polynomials which would vanish on that algebraic set. And homogeneous coordinate ring. Again, you take the graded ring and modulo out the homogeneous ideal. It's almost everything is like the affine case, but with homogeneous polynomials.